A storage tank contains californium-251, a radioactive element with a half-life of about 900 years. Let G of T be the percentage of californium-251 that remains at T years since the element was placed in the tank. A. Find the equation of G. B. What percentage of californium-251 will remain after 600 years? C. What percentage will remain after 3,600 years? So keep in mind, exponential function equation format, f of x equals ab to the x. Agreed? This is the exponential format that we typically use. And whenever we're talking about this types of problems, they're exponential format. So let's try to read it again. So I always recommend you read them at least twice. That way it makes a little more sense, all right? A storage tank contains californium-251, a radioactive element with a half-life of about 900 years. Let G of T be the percentage of californium-251 that remains at T years since the element was placed in the tank. So let's realize that it states half-life. Agreed? Half-life is a critical word. And let's also realize that it's half-life after or roughly about 900 years. Let's also realize that they want us to use the variables G of T. So it gives us G and T as our variables. And the percentage of californium-251 percentage, we're talking about percentage just for reference, it could be useful. Californium-251 is a brand name, sort of like going to the supermarket and buying something that has a brand name labeled on it. It's a type, in other words. In this case, it tells us what we're dealing with. It's a californium-251, meaning it's a radioactive element brand name. That remains a T year since, so T is important, it's our variable representation and represents years, since the element was placed in the tank. Okay, so let's go back and realize that half-life at 900 years is what is specified under. Half-life. And we're talking about percentage again, agreed? So half-life means 50%, so do be aware of that. Since it mentions percent, always refers to the half-life as being percentage, 50%. So we could probably convert this into a coordinate. So 900 is the years, that's the time t or the x representative, and 50% is the y value, or in this case the g value, because it's the representative of y. So 900 comma 50 would be our coordinate. Looks like we have very little information, agreed? Be aware, you know more than what you think in these case scenarios. If you're talking about percentage, what is the maximum amount that you typically have? Let's say you have a full bottle of water. How much water do you fully have? All of it, right? If you start with it from the beginning. So what if you start with a radioactive element that's presently all at the beginning? At the beginning would be times 0, right? What percentage will be at the beginning then? We would expect 100% to be there, right? So at time 0, initial, let's say you're starting at time 0 right now, you should have 100% of it. So at time 0, we have 100% of the radioactive element, or all of it. So therefore, we have another coordinate. At the beginning, year 0 or time 0, we had 100% of it. So we can probably start our equation with these two coordinates now, since we know the y-intercept, agreed? So g of t equals ab to the t is the format that we need in this case. Just a rough representation once again for what the formula should sort of look like. It's the same as f of x equals ab to the x, other than we're using g and t as our variables instead. And let's see, we know that in this case, the a value is 100. It's the initial amount, right? It's your y-intercept value. So g of t equals 100 b to the t. That's what we know so far, agreed? Once again, notice the 100 came from the fact that we have the y-intercept. So let's replace the y and x value, or t value in this case, with our second coordinate, the 900 and the 50. 50 represents the percentage, agreed? So that's g of t, that's the y value. And 900 represents the t, or the x, which is the exponent in this case. So we have 50 equals 100 times b to the 900. How do we solve for b now? Well, we can't get rid of the 900 yet because it would affect the 100. So the easiest thing is to get rid of the 100 first. It's multiplying with a b, so therefore we would divide it by 100, agreed? It's the easiest thing to do first. If we try to get rid of the 900 first, it'll be a little more complex than we want it to be. So 100 divided by 100 cancels each other out. 50 divided by 100, this is probably your calculator time. Let's see, calculator time. How does the calculator help us out? A very useful tool, right? In case we've forgotten. 50 divided by 100 is 0.5, or we can double check via our calculator. 50 divided by 100. Yep, that gives us 0.5. Okay, so we get 0.5 equals b to the 900 then. So how do we get rid of the 900? Exponential roots, right? How do we do exponential roots then? Well, exponential roots, it means you put a 1 over it. Agreed? So putting a 1 over it, but I may need more space on the 0.5 side. So 0.50, I have added more space. And 900, getting rid of it by reciprocal timing exponents. Keep in mind, it's an exponent over an exponent, agreed? So times 1 over 900. What we do to one side, we must do to the other side. Do notice there's only a 0.5. So that 1 over 900 affects everything on the left side. So if there was more, I would have to add parentheses. But there's only a single number, 0.50. In other words, 0.5. So we're taking it to the power of 1 over 900. This becomes a calculator work apparently as well, agreed? But let's realize that 900 times 1 over 900 cancels out. And our calculator time then. So 0.5 raised to the power of, and let's open up a parentheses. If you have a T84, you don't need parentheses in many cases. It automatically raises it up for you. If it doesn't raise it up, then you would have to put a parenthesis like what I have here. So 1 divided by 900, and hit enter. And there is your B value, 0.99923. So 3 nines, 2, and a 3. So let's copy it down. 0.999, then 23 is the V value. So we found the V value. That's the only thing we were missing for our formula. So our formula now becomes G of t equals 100 times 0.99923 raised to the power of t. So question A was A. Find an equation of G. We did. So question A completed. We found the equation. Question B, what percentage of the California 51 will remain after 600 years? Okay, so that's just a matter of plug and play now since we found the formula. B, G at 600 equals 100 times 0.99923 to the power of 600. And now we can plug it through our calculators. So calculator time once again. We have 100, we can do it all at once, times 0.1239, a 2 and a 3, caret key for exponents, and then put 600. Hit enter, and this should give you a value, roughly 62.99%, right? So 62.99%, or equivalently, if we round it up, 63% roughly. So there's our value. After 600 years, there's still 63% remaining. Wow, that's a lot. C, G at 3600. Once again, I welcome you to try your calculator. And notice that that's our T value, 3600, right? So calculator time once again. I can always hit second, enter, and it'll just copy the previous statement. Notice that it's the same equation. The only difference is 3,600 years instead of 600. I can push second, delete option gives me the option of insert, and put a 3 in there. And now it becomes 3600. So I can hit enter, and now it gives me the right value. So 6.247, or roughly 6.25%. So after 3,600 years, there's 6.25% remaining of that radioactive element. That's still significant, agreed? So be aware. We want to be careful on how we use radioactive material, right? So it could be terribly bad. For instance, if we're using it as an atom bomb, it's terrible because it doesn't just affect the area where it was dropped. Essentially, do remember, it could travel along the air maybe, right? And also affect the nearby areas. Well, for instance, in a tsunami a while ago in Japan, we were worried that it was going to reach the US as well, right? So it still travels through other mediums, so be aware of that. It affects us. So the way we use it is a critical part of our life. In a sense, it could be good or bad depending on the case, but it's not all bad. Be aware of that. For example, we could use nuclear energy to power up your house, right? As an example, you could drive a car for many, many years, probably in many cases more than what we could live. But the issue becomes, do we really want to power a nuclear power car that could be used in a bad way? That's the good or bad side of it. So something for you to think about. Another thing to be aware of. You're always getting radiation, right? But sometimes it's good radiation that comes from the sun, for example. So something to be aware. Take the good and the bad and put on a scale. But remember, try to use it appropriately and wisely.